You're welcome to the third session of business mathematics, where we'll be talking about the relative extrema. Right. The main idea is to delve into issues like maxima and minima, necessary condition for a relative extrema, sufficient condition for a relative extrema, and we'll look at the extreme value theory. Relative extrema. Right. Here we have a function, or I would say a diagram here that depicts the whole idea about relative extrema. Right. So we'll have a range of, say, alphabets here or function notations over here on the curve, just to illustrate what this relative extrema talks about. So I have on the x-axis A to C, and that consists of x1, x2, B, and what? X3. On this curve over here, I have the functional notations A to f of c. That is f of a to f of c. Now, we'll be looking at the point where a function is said to be increasing and a point where a function is also said to be decreasing. So you can see on this curve here, the function, right, or the product, assuming you are a producer producing, let's say, biscuits or shoes for school children, right? You can see that at some point you'll be making profits, at some point you'll be making losses, right? If it has to do with revenue, sometimes you'll be having, at a point in time, you're having the highest revenue. Sometimes you'll be achieving revenue, but it's not up to the target that you have, right? So here on the curve, you see that we have the curve increasing at a certain point, and then it is also decreasing at a certain point, right? So a function is said to be increasing on an interval r when for any two numbers x and what x2 in I, if x1 is what less than x2, then f of x1 is less than what x2. It says that the function is said to be what increasing. Looking at these two functions over here, x1 and x2, you could see that at this point here, f of x1, that's the function notation of x1, function notation of what x2. This x1 here is less than what the x2 over here. So at the point you can see that this function is what increasing. It is increasing at this stage. Looking at the second scenario, a function is also said to be decreasing on an interval I when for two numbers x1, x2, or we could say x3 here and then f x3 or fc. You could see that at that point f of x3 here is greater than f of x4, right? F of x3 here is greater than what? F of x4. So you can see that at that point, this point here is greater than what? This point over here. We could say that at that point, the function is also decreasing. You can see that it is decreasing. So let's say this side we have 4 here, this side is 2. It has decreased from 4 to 2, right? So as a producer, you could be making what? Profit or losses, right? This is just to explain what we talked about earlier. Another approach to determine whether a curve is increasing or decreasing within an interval is to apply differentiation, right? Which is quite simple and is based on the following rule. Let the function, say f, be differentiable on the interval a to b, that's a closed interval, if the differential of that function is greater than 0 for all x in the closed interval AB, then f is increasing. Right? So if the differential is greater than 0, then we'll say that the function is increasing. However, if the differential of that function f is less than the 0, then we say that for all values of x, right, on the interval AB, we say that the f is what? Decreasing, right? Or the function is decreasing. That is what it is trying to say, right? On our next slide here, we have a practical example or a scenario to show how you go about this relative extrema and relative extrema, right? That is minima and maxima. So given the function y is equal to 18x minus 2 over 3x cubed, determine whether the function is increasing or decreasing within the intervals at point what? A, say minus 2, 1, and point B, say 4, 7 on the x-axis here, right? So the graph of the function is shown below. So this graph here depicts or shows how this question here will be graphically represented on a diagram, right? So for this example, think of y as revenue and x as what? Quantity. So y here as your revenue, x as this here as quantity. Then we are looking at the range of quantities at which revenue is increasing or decreasing. Remember, as a producer, you could be achieving the highest revenue or the least cost, right? Your revenue can be increasing or decreasing, or you can be achieving profits at certain points, and then let's say at a certain point you'll be incurring losses, or yes, your profit will be lesser than what you had earlier. Okay. So what do you do next? If the function is given to you, you have to differentiate the function, right? That's the first step. So you differentiate the function, and then you have 18x minus 2x squared. Then what do? You put the first point, which is negative 2, 1, into that differentiated function or the differential. So in place of x, we have minus 2. Then that will give us this function over here, which is what? Or this final answer here, which is 10. 10 is also greater than what? 0. Like we say that at that point, the function is what? Increasing. And then when x is equal to 1, at that same point, we'll have 16, which is also greater than what? 0. Thus, f is what? Or the function is increasing on the interval, right? Negative 1 and 2, or at the point negative 1 and 2. When x is equal to what? 4. That is on the second point that we have, 4 and 7. If it's substituted in place of this differential here, we're going to get minus 14, which is also less than 0. And then when x is equal to 7, substituted in the same function, we'll get minus 8, which is less than 0. So we can say that at that point too, the function is what? Is decreasing on the interval 4 and 7, right? Let's take a look at this example 2. Given the function y is equal to x cubed minus 5x squared plus 7x plus 2, 3, that's 23. The first thing is the first step is to differentiate the function. The differential of this gives you 3x squared minus 10x plus 7. What do? Just equate the differential, or what you differentiated into, or differentiated what you differentiated, equate it to 0, right? So differentiate the function, equate it to 0, and that will give you these terms over here, right? So if these functions over here or these terms over here are also equated to 0, or we make s the subject, we are going to get the values of x to be 1 and then what? 7 over 3. This is just to show how it is going to be done or illustrated on the graph, right? So we have what is called a relative extrema, relative minima. Okay, a point where functions reaches a highest value compared by nearby points. If, say, f of x has relative maximum at x, which is equal to a, then f of a is greater than what? F of x for all nearby x points. Relative minima, a point where the function reaches its lowest value compared to nearby points if f of x has a relative maximum, a relative minimum at x is equal to b, then f of b is less than what? Less than or equal to f of x for all nearby points, right? So after doing that, then we will have our differentials here. We just substitute these values into it. We have 7, we have negative 1, we have 4. So at this point, you can see that this is greater than what? 0. 7 is greater than 0. It is increasing at that point. Negative 1 is less than 0. We would say that at that point, it is what? It is decreasing, right? And then 4 is greater than 0, also increasing at that point. So if you have the function, just differentiate it, equate it to 0, get the values of x, right? We'll move on to the types of relative extremes we have. The first one is relative maxima or maxima, and then we have relative minima or minimum. Okay. So Say we have this graph here also, which also shows how we are going to deal with what is called the minima and then the maxima. Okay. So say for a range of products, maybe you are a producer producing, say, pens or phones for students or workers at a particular financial institution. Okay. At a point, you'll be making the highest profit, right? At some point, you'll be incurring losses, but that is the least possible cost, right? If it has to do with profit, you'll be getting the highest profit or the least possible cost. So let's take the maxima as profits, highest profit, minima, say minimum cost, right? Maxima, say maximum profit or maximum revenue, minima, say minimum cost, right? So we have the local maxima, minima, global maxima, and then the differential of a function where it doesn't exist, right? So maxima has to do with maximum point, minima has to do with minimum point. At this point, we would say that say we have a class of students, right, who are taking exams or for the sake of maybe their end of sem, right? We have, let's say, three classes. Okay, we combine those three classes together, and we have maybe three students, that's one from each class, topping the class. Let's say group one, someone top group one, group two same, group three same, right? That is, they are called the local maxima. So locally in their group, they top, right? But if we bring all those people who top in their various groups together to get the overall best students or the overall top scorer, then that person, or at that point, we will say it is a global maxima, right? And then we have the minima as well here. So, like I said, maxima has to do with maximum point, minima has to do with what? Minimum point. Because as a producer, or let's say as a manufacturer, we would want to achieve the highest profit or possibly incur the least costs, right? So the highest and lowest points are called point of relative extremum. The curve is locally maximum or minimum. Under this relative maxima and minima, we have conditions under them, and that is what we have here. The first one is called the necessary condition for relative extrema. The idea about this rule or this condition is that when you have a function, or you are given any function, or you find that function, differentiate the function, equate it to 0 to get the values of x or the value that you want, right? So as local minima or maxima, it is called a relative extreme. Differential is equal to 0. However, cannot tell exactly whether the point x where f of x, right, f prime of x is equal to 0 is indeed a maximum or minimum. We need another rule to help us. So say we've been given a range of production. Say we are producing pens for a particular primary school, and the range of product is to produce 0, that is nothing, or produce 130 pence for them, right? If we have a given function like that and we differentiate the function, equate it to 0, and then we get quantity to be produced for the school as, say, 30 or 20, right? It means that if we produce just 30 units out of that range of product 0 to 130, that 30 will give us the highest revenue. Let's say we're talking about revenue here, or to give us the maximum revenue, right? But you are given a range of production. You can produce 0 to 130. Well, you can't just consider the 30 to be the one to give you the highest revenue, right? So we need another test to confirm or to show that indeed, if you produce just the 30 units out of the range 0 to 130, that you can consider 100, 120, and the rest, this second test will tell us that indeed that point 30 will give us the maximum revenue or the maximum profit, right? That is called the sufficient condition, right? This is also saying that take the second derivative of what you differentiated. So here you do the first differential, and what you get, differentiate it again here. That's what this is saying. If you take the second derivative and it's less than 0, then the point is a relative maximum point at that value or the other variable, say a or x. But if you take the second derivative of what you differentiated and it's greater than 0, then the point is what? A relative minimum, or it is a relative minimum point, or a minimum point there, where the second derivative at y of y at a, right? So basically this is the idea, general idea, but take the second derivative of what you have. If it's less than 0, it is a maximum point. If it's greater than 0, it is a minimum point, right? On our next slide here, we have a practical example to show how you go about a minimum and maximum point. So given the function y is equal to 2x squared minus x4, find a point at which either minimum or maximum occurs, right? Indicate whether a relative extreme from the question is whether a relative extreme from question is a relative maximum or minimum point, right? So what do? We have the function already. Differentiate that function, right? This is what we have here after differentiating it. Find the values of x, right? So we are saying that this is the point where the relative maxima and minima occurs, right? So what do? We do the second test, right? To establish f of x attains a minimum or maximum values, we apply the third rule as a sufficient condition. Take the second derivative of this 4x minus 4x to the power third, and the differential of that will give you this, right? Okay, now what do? The next thing is that put this value 0, 1, -1 in place of x over here. First, at x is equal to 0, we had it to be 4, which is greater than what? 0. If it's greater than 0, it is a minimum point. Here we have 1, into it we had a final answer of -1, which is less than 0. At that point, the function is a maximum point, sorry. At x is equal to -1, after substituting it, we had -8, which is also less than 0, and it shows that that point is indeed a maximum point, right? I hope we get this general idea about relative extrema. Let's look at this illustration or this example that will help us to apply this in the business sense, right? So suppose the price is given as P is equal to 80 over Q. Sorry, 80 minus Q all over 4 for the range 0 to 80, where Q is the number of units of product. At what value of Q will maximum revenue be attained? Maximum revenue. What is the maximum revenue, right? This is an application of the relative extrema. So we're talking about maximum revenue or total revenue. How do you get total revenue? It is price times quantity. We have the price function here to be 80 minus Q all over 4. We just multiply that by Q, and then we have 80Q minus Q squared all over 4, right? At the quantity where maximum revenue is attained, the differential of the total revenue function, that's what this is saying, is equal to 0. So what do? Differentiate this function, equate it to 0 to get the quantity, right? So on our next slide here, the differential gives us what? 80 minus 2Q. If it's equated to 0, our quantity will give us 40. What does this mean? It means that looking at this range from 0 to 80, if we produce just 40 units of the product, we are going to achieve that maximum revenue or that highest revenue. So given the nature of the revenue function, then at quantity being equal to 40, revenue could be minimum or maximum. To establish whether it is a maximum or minimum point at Q, which is equal to 40, we use the second derivative test, i.e. the sufficient condition. Take the second derivative of the differential. The differential here is what? 80 minus 2Q. If we differentiate this again, second derivative, it gives us -2, which is less than 0. What is it telling us? It means that that point is indeed a maximum point. It also means that Right, if you produce just 40 out of the range of products 0 to 80, we will get the highest revenue. Thus, Q is equal to 40 at a quantity level which generates the maximum revenue possible, right? Revenue is equal to what the total revenue function is 80Q minus 40 all over what? 4. 80Q minus Q squared all over 4. That's the revenue function. To get the maximum revenue, we just substitute the 40 in place of Q. We have a maximum revenue of 400. In this sense, it means that if we produce 40 units or 40 products, right, we are going to achieve or attain a highest or the maximum revenue of $400 or 400 Ghana cedis. In the sense, this is one of the reasons why we have to learn differentiation, right? So as you can solve problems like this in the business sense. So this is how you apply it in the business perspective. We'll move on to what is called the extreme value theorem. Extreme value theorem has to do with situations whereby we deal with not only the Q that we calculated for, that is the 40. We are going to consider 40 and then the extreme values of the range. Remember, the range was 0 to what? 80. From the question that we had, 0 to 80. We're not going to consider just the 40 over here. We'll consider the 0 and then the 80 as well. That is what the extreme value theorem is saying. If a function f is continuous in a closed interval ab, then the function has both a maximum value and a minimum value on that interval, closed interval ab. Note that one should guarantee that the function is continuous. One, the function is being analyzed in a closed interval. Two, the symbol a, that is into brackets ab, implies a closed interval and includes the endpoints ab. So from that question that we did earlier, the endpoints is 0 and 80, right? Whereas ab implies an open interval and excludes the endpoints ab, right? So this is just explaining what we did earlier, that we are going to consider the extreme values, not just the 40 units that we had, right? So looking at the same question here, right? We had Q to be 40 after differentiating it, equating it to 0. We had 40, that is for our Q. What to do with that? However, since the analysis is being carried over a closed interval, we need to verify the endpoint, that's the closed interval or the endpoint, sorry. Q is equal to 40 indeed yields the absolute maximum revenue. How about the 80? How about the 0 as well, right? So we'll consider 0, we consider 40, that's what we calculated for, and we consider the 80. The closed intervals are 0 and then 80. So we'll put the same quantities here into the total revenue function. So if total revenue is equal to 0, then we have 0 here. If the total revenue is equal to quantity is equal to 0, we have revenue to be 0. If quantity is equal to 40, then the total revenue will be what? 400. If the quantity is 80, we produce all the 80 units, then we'll get the revenue, total revenue of 0. You see, it's simply telling us that after considering all the extreme values, the maximum point is at what? To produce quantity of 40 units to achieve the highest revenue. So thus, the maximum revenue is attained at quantity 40. So it means that as a producer, if you produce more, it doesn't mean you're going to achieve or attain the highest revenue, right? Application of this relative maximum and minimum, right? So suppose C is the total cost function of Q, unit of a product, where this is the what? Total cost function. At what level of output Q will average cost per unit be minimum? And then what is the minimum value? We've been given the total cost function to look for or to calculate our average cost. We know that total cost is what? We know that average cost is total cost divided by quantity. So we'll just divide this total cost function by quantity. Then we have this function over here, right? Same application on what we did under the extreme value theorem or relative extrema. We have the function now. We are going to differentiate the average cost function we have here and equate it to 0, right? So after doing that, we have this, and then our quantity will be plus or minus 40 because of the square here, and then we have a square root here, right? We are going to get plus or minus 40. And then since we can't produce negative units, right, we can't say we are producing negative 40 units. No. So it is Q is equal to 40. So to confirm whether our average cost at Q equals 40 will give us the least cost or the average cost, the second derivative test is applied, the sufficient condition. Take the second derivative of the differential, which is what we have here. If you differentiate this function over here, you are going to get 800 q to the power negative 3. 800 q to the power negative 3 here is greater than 0. And that shows that at that point, it is a minimum point. So therefore, the minimum average cost occurs at 40 units indeed, right? The value of the minimum average cost at q is equal to 40 simply tells you that put this quantity of 40 into that average cost function, and then you have this 23 over here. This is also another example under relative extrema where we have to apply what we've learned. So the Visa TV company currently has 100,000 subscribers who each are paying a monthly rate of 40 Ghana cedis. A survey conducted reveals that there will be 100 more subscribers for each 0.25 decrease in the rate. At what rate will maximum revenue be achieved, and how many subscribers will there be at this rate? It's talking about maximum revenue, so total revenue, which is price times quantity, right? We don't know how the number of times that this rate will be reduced by 0.25. So let's x the number of times rate is decreased, right? So you know that price is the same as the rate we have here, right? You see that if the rate is 40, it is going to be reduced by 0.25, right? So minus, right? The rate is now 40 units, or the 40 Ghana cedis minus the 0.25 decrease times x. You know the number of times is going to be reduced, right? And then we have the number of subscribers, which is also representing a quantity, right? They are saying there are 100,000 subscribers, and if it is reduced by 0.25, we have 1,000 more, right? So it is 100,000 plus 1,000x. Okay, so we can find a revenue function which is saying that it is price times quantity. Multiply this by that, and that will give us this function over here, right? The next thing is to find the maximum revenue, right? What do you do to get the maximum revenue? You are going to differentiate the function that we had earlier, i.e. this function over here. The differential of this total revenue function gives us what? The function that we have here, that is saying that the differential is 15,000 minus 500x. Equated to 0 here, we'll have our x to be 30. It means that if the rate is being reduced 30 times, we'll achieve what? The highest revenue, or the maximum revenue. But how are we sure about this? Because the company can also make the subscription free, right? So the second derivative test is going to confirm that if we reduce it 30 times, that will give us the maximum revenue. So if you take the second test, or the second derivative test on this differential, we are going to get negative what? 500, right? Negative 500, which shows that that point is a what? Is the maximum point, right? It's a maximum point. So that's at x equal to 30, the relative maximum revenue is 13. However, this is the range. So we can reduce it 0 to 160 times. So we are saying it should be reduced by 30 times to achieve the maximum revenue. But this is the range. How did you get the 160? It's just the rate of 40 cedis divided by the decrease 0.25. That will give you 160. That means that the company can choose to set x is equal to 0, meaning no reduction, or 160, that is, they charge nothing, making the subscription free. Okay, we just have to test the revenue, particularly at x is equal to 0, since it is obvious revenue is 0 at x is equal to 160. What do? That is the extreme value theorem. You put this 0 in place of the revenue function, we are going to get 4 million. Note that this is a revenue function. This function over here, you are going to get what? 4 million. If you put 0 there, if you consider the 30 that you calculated for, that you are saying that if you reduce it by 30, that will give us the maximum revenue, and we've confirmed that by doing the second test, you are going to get what? 4 million. okay, plus this, and that should give you 4.225 million. Okay, so 0 gives us 4 million, 30 into the revenue function gives us 4.22 million. You can see that the 4.22 million is higher than the 4 million. Thus, the revenue is attained when the current rate is reduced 30 times, right? So if we reduce it by 30 times, we will achieve the maximum revenue. You can try with the 162. You can put the 160 here into the revenue function. You can see that it will be less than that of the 30, or it will be less than the 4.225. Okay, so therefore maximum revenue is equal to 4,225,000 Ghana cedis. Right. This is another example on the relative extrema, which is also the application of the minimum and maximum. Right. You can also take a good time and then try this. Right. If you have any question, you can put it in the comment section, and we'll be able to help you gladly. So you can try this at your convenience time. Let's look at the final parts of the session, which is also the application of what we've learned under relative extrema. Right. Suppose n the number of recipients of the healthcare benefits after t years, where n is in thousands of elderly people and given as n is equal to t cubed over 3 minus 6t squared plus 32t. The range is 0 is less than t is less than what? 12. At what values of t will the number of elderly receiving benefits start to fall? Right, what do? You've been given this function over here. Looking at the first condition that we learned, that i.e. the necessary condition, it says that when you're given the function, differentiate that function, equate it to 0, find the values of what you are being asked for, right? At what values of t? So we are looking for t here. Differentiate this. T to the power third, or t to the third over 3 gives you t squared. That's the differential. The differential of minus 6t squared gives you minus 12t. The differential of 32t gives you 32. If you equate this to 0, either by using methods of completing squares, right, using the quadratic equation formula or your calculator, then you can get the values of t to be t is equal to 8 and t is equal to 4. That's the values of t, right? You could also use the quadratic equation formula, which is saying that to find it is minus b plus or minus root of b squared minus 4ac all over 4a, right? Where you are going to use this function over here, right? So your b is what? Is minus 12. Your a is 1 here, the coefficient of t squared. B is negative 12, the coefficient of minus 12t. And then c is the constant 32. That should give you the same values, 8 and 4 here. So the values of t, where the number of early receiving benefits will start to fall, it is at what? 8 and then 4. Thank you for this session. Thank you for participating as well. I'll urge you to subscribe to this channel, and then if you have any further questions, you can put it in the comment box, right, or in the chat box. Thank you and have a good day. Meet you next time in the other sessions. Bye.